Hello, welcome everybody to this new series that we are starting here at CCAM. We are all suffering from these pandemics and its low evolution, so we are still, unfortunately, having to handle or cope with it in the coming months. And at CCAM, during all this period, we are trying to see how we can still serve the community by creating formats, ways of interacting that necessarily have to be or cannot be face-to-face. And out of the different initiatives that we have started to develop, we thought that, we are all affected, but this situation has a big impact on early stage researchers in our community. For PhDs and postdocs, the inability to attend meetings, to get to know other people, other students, established scientists is a drawback in both training and also in how they start building their networks and also start to learn how to work as researchers. And that's why we thought it was appropriate to put forward a series that is devoted to them, or that put them in a central place within an event that, in any case, as always for CCAM, is open to everybody. So this is the first of a series of events that that will happen on average once per month, in principle, until the summer, and you can see them already. The list is already available on the website. In each session, we want to focus in one type of area and we invite already a consolidated researcher to provide a lecture on an advanced topic of simulation, and also bring young researchers that then can present their work. So this is organized. We try to keep, even if being connecting remotely, it's difficult. We try as much as possible to think on formats that are innovative and that can try to promote as much as possible informal interaction to keep the CCAM spirit of our events. And that's why we structure these events or these sessions in a first part where we have in this Zoom environment that by now is familiar to all of us, a presentation, as I said, by an expert, and then there are 2 additional presentations by young researchers. And afterwards, there is a second part where we will move to using this gather that provides a much more informal and interacting environment. There you will be able to see, and all posters that have been presented will be presented by attendees, and you will have there the opportunity to talk, to listen to them, and to interact with all the people that are attending this event, which is not the case now. Unfortunately, I wanted to remind you that as for all CCAM events, in the webpage for this event, you as a registered participant, you can enter and have access to a PDF or a booklet where you have all the information about participants and titles and abstracts for all posters, and also the PDFs of the posters can be accessed through this event webpage as well. So that may help you to access quickly, to see what is around, and pre-select posters that you may be more interested in going first to interact with presenters in this gather session. So let's start with this first part of the event. As I said, we have today is about activated events, the overall theme of the session, and we have 3 speakers. Let me just also, since we have to know to get to know to interact through this webinar session, I wanted to explain you how this is going to work, this first part, so that we know how to behave and try to get as much as we can from it. first of all, the meeting will be, this session, the Zoom part will be recorded, and so that later on we will make it available through the CCAM YouTube channel, so that then this is something that will be also useful for those of the community who are unable to join us today. The video, your video is disabled, so you cannot activate it through this Zoom session. And also there is no possibility to chat. So the way to interact in this session is that there will be this Q&A panel that you have where you can pose your request to ask a question. So at the end of each of these 3 presentations, during the presentation, if you want to ask a question, you should indicate in this Q&A, I want to ask a question, so that then we will have the whole list. And then when the Q&A period starts that I will be sharing, I will be giving you the floor. I will say, well, now this person can ask a question. And then because we have the list, just before that, you will receive from the technical team, you will receive a request to unmute yourself, and then you will be able to unmute yourself so that then you can ask the question when I ask you to do it. Okay, so that's it's not an ideal way to interact, but let's see how it goes. We have organized this first part of the session in such a way that there are the 3 presentations, but then there is enough also time for Q and to ask questions, to have a dialogue. So I hope that, I mean, just that this is very interactive. Yes, I encourage you to ask questions, and then at some point, if not all of them can be addressed now, we in any case have the gather session where you can also approach the 3 speakers who will be there to continue with more informal discussions. Okay, so we will start now. Let me introduce the person that you see here with us today. So I have with me Sarah Bonella, the CCAM Deputy Director, with obviously with whom we have been driving this preparation, and she will be here also providing support and will be around also in the gather. And then the 3 speakers today are Christoph Delago from the University of Vienna, and then afterwards we'll have a second speaker, Luigi Bonatti from the ETH Zurich, and Jan Liang, who is working at ICAM in Bochum in Germany. Okay, so let's hope that this is an environment that is dynamic, that you find it that is attractive. And as I said, in order to make it really successful, please be as interactive as possible within the constraints during both now the Zoom session and then afterwards in the gather, in the poster session. Okay, so without any further delay, so I now give the word to Christoph to provide the first lecture. So Christoph, please.
Well, thank you very much, Ignacio and Sarah and everybody for organizing this event. It's really an honor to be part of this. But I should also complain because you put me in the old generation in a mixed generation event. I guess objectively that's true, but did you really have to say it so bluntly? Anyway, I really look forward to this event. In particular, I look forward to the coffee break. I got myself a nice Faschingskapfen, which I will eat during the coffee break. So my job here today is to introduce the problem of rare events. Let me share my screen. I can do that. So I will talk about rare events. In particular, I will focus on methods. So this is a methods-focused talk. Of course, over the last decades, many methods have been developed to address the rare events problem. So I will provide a personal view. I hope that I won't offend anybody by leaving out certain things. So let's start by watching a movie. This is a movie that my former doctoral student Wolf Lechner made for his PhD. He is now a professor at the University of Innsbruck. You see a bottle of water here. And now he hits the bottle on the table and you see that it freezes. So now it's solid. So what you had here in this bottle before Wolfgang hit the bottle on the table was supercooled water. You can actually do this very easily by putting some regular water in the fridge. Works also with other liquids, beer, for instance. And then you can do this little trick. So what you have here is water that is below freezing, where it is supposed to be, ice. Now, this is not something new that Wolfgang discovered here. Actually, the first person to observe that you can have a supercooled liquid was Daniel Fahrenheit, who in 1721, in the early days of March, actually this is almost precisely 300 years ago, he made the observation that if you take liquid water and put it in a container and then you put it out during a cold night, he observed that the water remains liquid even if it's below freezing. And what he observed is that he could cool the water down to -10 degrees Celsius, actually quite a cold night for early March. Maybe climate was colder back then. Anyway, so he also observed that if you disturb this water with a little ice crystal, it freezes. Also, he stumbled holding this container in his hand while walking from one room to another, and it also froze. So apparently, this is a way to make the water freeze and to allow it to go to the thermodynamically more favorable state, which is under these conditions is the solid. Now, after Fahrenheit, many people repeated the experiment. For instance, not too long ago, Stöckel, Weidinger, Baumgart, and Leiser, they put little water droplets in an electrodynamic balance and waited until these little droplets froze. Now, by repeating these experiments many times, you can determine the nucleation rate. So this is the number of freezing events that you observe per volume and per time as a function of temperature. And this is what they found. Different experiments give slightly different answers, but they find that to get an appreciable nucleation rate, a measurable nucleation rate, you really have to cool down below freezing by a lot. So in these experiments, they cooled down to temperatures below -34 degrees. Here, these data here are for D2O. I'm not sure, but I think the current world record of liquid water is -46 degrees Celsius, which means that for temperatures that are just below freezing, the crystallization of supercooled water happens only very rarely. In fact, Carlos Vega and collaborators, they have estimated that if you wait for a homogeneous nucleation event to happen in water, that the temperature of -20 degrees Celsius, then you will observe only one crystallization event in the age of the universe in the entire hydrosphere of the Earth. So this is really what I call a rare event. Now, why is that? Of course, we know that in a qualitative way, we can understand why the freezing and other phase transitions are so rare in the framework of classical nucleation theory. Here, the idea is that the transition from a metastable phase to a thermodynamically more stable phase occurs via the formation of a localized nucleus of the stable phase in the metastable phase. Now, if you think about the free energetics of this process, then you realize that there is a free energetic cost to produce such a nucleus. And this cost is associated with the surface tension with the free energy of the interface between the two phases. Now there is also a gain because you transform some of the material into the more stable phase, and that's where you have a gain. The thing is that the free energetic gain and the free energetic cost, they scale differently as a function of size. For the surface part, that term scales like the square of the radius, and the volume part scales like the third power. That's the red line here. If you sum them up, you find that there is a curve with a barrier, and it is this barrier which makes it hard for the system to move from the metastable to the stable phase, because a rare fluctuation is needed to overcome this barrier. And if you do what classical nucleation theory tells you to do, and you assume that the nucleus that forms is spherical, which it is not. Yeah, here you can see a little ice nucleus that forms in water. You get an expression for the rate at which this nucleation happens, and you have this famous exponential factor here that tells you that the rate is very sensitive to the height of this barrier, and if this barrier here is high compared to KT, then the nucleation rate is very low, and you have to wait for a long time for this event to take place. Now you also have a pre-exponential factor here. You often hear this pre-exponential factor is not important, but it turns out that under certain circumstances it is important, and it can actually change by orders of magnitude, just like the exponential factor here. Now imagine that you would like to simulate this process in a computer, for instance, to find out whether the assumptions that you make in classical nucleation theory are correct. You would like to find out the mechanism and possibly also to calculate rates for this process. Now, the obvious tool of choice is molecular dynamic simulations. And now let's imagine that we try to do such a simulations for conditions that are close to the conditions in which, for instance, this freezing experiment was done. Now, if we imagine that we do such a simulation with 1,000 water molecules, you could take 10,000 or 100,000, doesn't matter. So this is a volume of about 3 × 10⁻20 cubic centimeters. If you assume that you have the nucleation rates of the experiment, this means that you will observe in this small volume, you will observe one event only every 10 to the 15 seconds, which means you need a lot of molecular dynamic steps before anything of interest happens. And this is exactly what a rare event is. Such rare events are not particular to phase transitions. They occur in any process where regions in phase space of low probability, or equivalently of high free energy, have to be crossed. These processes include chemical reactions, transport processes on surfaces or in solids, phase transitions, like I mentioned, biomolecular rearrangements like protein folding, or transport processes through membranes. So what I would like to do in my talk is to tell you about methods that you can use to address this problem, because you have a problem here. You will not able to wait for 10 to the 20 or so molecular dynamic steps in order to see just one of the events that interest you. Now, this is the prototypically rare event process, and all rare events can be understood in terms of the ideas that I'm going to introduce now. So imagine you have a one-dimensional system described by the coordinate q, and then you have an energy surface. This energy surface could also be the free energy surface that you obtain by projecting onto this one-dimensional coordinate q here. Now, in the system, there are two stable states that are long-lived in the sense that if you put the system either in state A or state B, it will remain there for a long time before eventually moving, hopping over the barrier onto the other side and changing from one of the states, let's say A, to state B. This hop over the barrier is rare if the free energy, if this energetic barrier here is high compared to KT. Why? Because if delta F, if this height of the barrier is large compared to KT, this means that you are here on top of the barrier only very rarely. If you were there more often, then the free energy would not be high. Having a high free energy or is a synonym of saying that being at these values of Q is happens only rarely. Now, if you follow the motion of the system, you could imagine, for instance, that the system follows some kind of Langevin equation. If you follow the motion of the system in terms of this coordinate Q as a function of time, then you might observe something like this. So you have fluctuations of the system about the minimum A, and then once in a while, the system hops over to the other side of, to the other well, remains there for a while, and then by chance manages to overcome the barrier again and to hop back. So what interests you are these transitions between the two stable states. Now, if the waiting time between the transitions is much longer, by orders of magnitude, say, much longer than the time you actually need to cross the barrier when you do it, then we say we have a time scale gap. And it is this time scale gap which creates a computational problem. Why? Because imagine you do a molecular dynamics simulation, then the time step that you need to use is certainly smaller than this molecular time scale that is needed to go over the barrier. This will also be the time scale of the typical time scale of the oscillations in the two wells. Now, since this time step needs to be small compared to the mole, it will be even much smaller than the reaction time, the time that you have to wait. And so it is the gap in time scales which creates a computational problem, just because the waiting times between events of interest is so long. So if you try to simulate a rare event process with straightforward molecular dynamics, you will spend a lot of your computing budget waiting for things to happen. And of course, you don't want that. So you can do better. And one approach to do better is the so-called Benegender approach, which is based on the observation that in going from A to B, you have to pass through a transition state. Now, if you put your system on this transition state, from there, it should be equally likely to, for the system, if you give it a push into a random direction, to fall back into A or to fall into B. So from the transition state, the two states are, in a sense, equally accessible, and you don't have to wait for a long time for the system to do at least half of transition that you want to see. So the idea here is to put the system on this transition state and then let it go from there in forward and backward direction. And in doing that, you will generate the trajectories that you can then analyze to understand what's going on. So this idea that was born in the 60s and 70s can also be made precise in order to compute reaction rate constants from such an approach. And the tool that you use to do that is the time correlation function. The time correlation function C of t, which you obtain if you correlate the population function in time with it itself. So instead of looking at the trajectory of the coordinate QA, you translate this time evolution into the time evolution of a characteristic function A, HB, in this case HB, which tells you if the system is in B or not. Somewhere you have to put a boundary. Let's put the boundary here at Q star, and if Q is larger than Q star, then you say the system is in B, corresponding to an HB of 1, and if it is in A, then HB has a value of 0. If you compute the time correlation function of this population function here, like I've written down here, then you can show that for times that are larger than the molecular time, so the time that is needed to cross the barrier, then this function should behave exponentially as dictated by the phenomenological rate equations that depend on rate coefficients, reaction rate constants, like the rate constants KAB here. Now, if you look at these time correlation functions for times that are short compared to the reaction time, this time correlation function should be linear in time, and correspondingly its derivative should be constant, and the value of the derivative then is the reaction rate constant. So this really gives you a recipe to compute rate constants, and this recipe consists of two parts. One part consists of computing the free energy as a function of the reaction coordinate that you have selected in order to separate the two states, to discriminate the two states from each other. So this, what you can see here on top is just the likelihood to observe the system at the value of the coordinate Q that corresponds to what you call the dividing surface. So this is a purely static quantity that can be computed just by sampling static configurations without the need of generating dynamics. And this factor here that can be computed from the free energy is complemented by a dynamical correction factor, which is obtained by starting trajectories at the dividing surface and watching what they do. You give them random momenta drawn from a Maxwell-Boltzmann distribution, and then you let them go, and some of them will recross the dividing surface, some of them won't, and as a result you get this dynamical correction factor. Now, how can you generate the free energy? Here, for instance, by using umbrella sampling or other methods, like, for instance, by using constraints like you do in the Blue Moon ensemble. Now, as a result of such a calculation, you get this function k of t here, which is the derivative of the time correlation function. This is also called the reactive flux. And the reactive flux has the property, if you have this separation of timescales, that it has a transient behavior here at the beginning on timescales that are of the order of the timescale that you need to cross the barrier once you have decided to do so. But when this transient behavior is over, the reactive flux settles on a value that corresponds to the reaction rate for the transition from A to B. Now, this reaction rate is always smaller than the so-called transition state theory estimate of the reaction rate constant, which neglects the fact that sometimes these trajectories turn around more than once often and cross this dividing surface, which leads to a reduction of the reaction rate constant, which is measured in the so-called transmission coefficient, a number that is equal or smaller than 1. Now, you can even simplify further, for instance, by assuming that there are no such recrossings of the dividing surface. This yields the so-called transition state theory estimate. And in order to compute this reaction rate constant, you don't need to do any dynamics anymore. All you need is the free energy, and then you need the average velocity of the reaction coordinate at the dividing surface. And this is something that you can compute from the Maxwell-Boltzmann distribution, and you don't need to do any dynamics. You can even simplify further by assuming that all trajectories has to go through a transition state corresponding to the saddle point, to a saddle point in the potential energy surface. If this is the case, and you can approximate the saddle point harmonically, and also using a harmonic approximation for the reactant state, you get an expression here that has what's called the Arrhenius form, namely it has the exponential of minus the height of the potential energy barrier now over kT, multiplied by a factor that depends on the frequencies, so on the curvatures at the transition state and in the stable state. You can view this factor here, which is often called the pre-exponential factor nu. You can view this as a entropic factor that tells you how wide the bottleneck is that you need to cross here when you go through the transition state, right? So if you have a large frequencies, that means you have a steep, a very strong curvature at the transition state. That means that the passageway that lets you go from A to B is narrow, and that's what makes it hard to go through, and that reduces the transition rate constant. Anyway, so this is the famous Arrhenius law. It's also called the Van 't Hoff Arrhenius law. And the interesting thing is that Arrhenius apparently never wrote it down. It was written down by Van 't Hoff. Now, as I said, it is often said that this pre-exponential factor is unimportant, but that's not true. And there are effects which are solely due to this pre-exponential factor, and one of them is the famous Kramers turnover that goes back to Hans Kramers, who in 1940 developed a theory for calculating the rate for escape from a well. And he found out that for a given potential energy surface, there is a strong dependence of the rate on the coupling to the environment. Or in other words, there is a strong dependence of the rate on the friction. For very small values of the friction, the transition rate is small. Then it grows as you couple the system more strongly to the environment. So how can that be? Well, you can understand it in two ways. By the way, it's explained very nicely in David Chandler's so-called Lda lectures that he wrote in 1998. And this picture is actually taken from these lectures. At low friction, it's hard for the system to collect enough energy from the environment to cross the barrier. Or if you think in terms of being at the barrier, it's hard for the system, once it crosses the barrier, to dissipate the energy away, and only if the system is able to get rid of the energy to transfer it into the environment, then the system will manage to settle in one of the stable states. As you increase the coupling, as you increase the friction, the transition rate goes up, expressed here actually in terms of the transmission coefficient. But remember, the energy barrier is the same, so this is the only thing that changes as you change the friction. As you increase the friction, it goes through a maximum, and this maximum is what's called the Kramers turnover. Now, if you increase the friction more, you will have the opposite effect. The transition rate will decrease, and it decreases because trajectories that go over that cross the dividing surface will do that many times if the friction is large and the motion and the diffusion constant is slow. So you have a In the high friction regime, the transmission coefficient or the rate becomes small again, but for a completely different reason. So this is an effect. This is solely due to the pre-exponential factor rather than to the factor that contains the barrier. Now, usually it is hard to measure this effect because most often it is difficult to control the friction separately from the barrier. So changing just the friction and leaving the potential energy barrier the same usually does not happen. But here in this experiment that my colleagues at the ETH did not too long ago, they can do exactly that. So they put a little glass particle into a bistable laser trap. And you can see the potential, a projection of the potential caused by these, produced by these laser beams on the particle here. So you have two stable states separated by a barrier. And if you follow the dynamics of this little glass bead, about 100 nanometers large, and they can measure its position very precisely. It oscillates here actually with a frequency of hundreds of kilohertz. If you follow the motion of this particle in the direction of in which you have the bistability, then you see these rare transitions from one side to the next. And from these traces, you can compute the rate for transitions between the two wells. And here the pressure it is the quantity that controls the friction. You can vary the pressure, so the amount of air that you have in the container where you do your experiment, and by varying the pressure, you can vary the friction and observe exactly this Kravers turnover. Now, so the one remark I should make here, it's perhaps an obvious remark, but I would like to make it nevertheless, because often I have discussed with my students about this. And the thing that I want to say is the following. The free energy that one often talks about is not a unique quantity in the sense that the free energy does not exist. The free energy is always considered as a function of some coordinate, of some constraint that acts on the system, and this carries this non-uniqueness of the free energy is something that you need to be careful about. Now, imagine that you here's a little example. Imagine that you have a potential energy surface that looks like this, like the red curve here. So you let the system evolve according to some set of rules that produce the equilibrium distribution, and the distribution that you then get has two maxima, one maximum here at the position of one minimum and the other maximum at the other minimum. What I have used here for this little example is the energy, or 1 minus q squared. So this produces these two minima separated by a barrier of height 1. Now, you can now carry out a transformation of variables to a new variable, and the new variable could be equally valid as a reaction coordinate, for instance. And if you do this transformation in the right way, for instance, by using this transformation here, which is indicated as a black line, you find something that has no minimum, and only one maximum. The corresponding free energy is harmonic. Now, in this case, you would say, okay, here I have two states separated by a barrier. In this case here, you would say, no, I don't have a barrier. I just have a single, my system lives in a single state. But that might be completely wrong. And to see it only, if you look at the dynamics, the the two distributions that you see here are obtained from the same for the same system, just by looking at the system, at the statistics of the system in a different way. And this looking in different way, it corresponds to carrying out this transformation of variables, and this transformation shows up as the Jacobian of this shows up as a Jacobian in the free energy. Now you may say, well, this is trivial. Yes, but this is something that one should keep in mind when one talks about free energies. The free energy is always a free energy of something. Obviously, if you look at it in a dynamical way, one time looking at the coordinate q and one time looking at the transformed coordinate z, then you see some bistable behavior here too, but you don't see it if you just look at the distribution. Obviously, if you look at it from a dynamical point of view in terms of a time correlation function, then you will get the same result for the time correlation function and its derivative in both cases. Why? Well, if you think about it in terms of the Benegender approach, then you have a Jacobian in both factors, but they cancel each other exactly. And that's why the transition rate does not depend on the particular coordinate that you use to describe the dynamics of the system. So there is some ambiguity here, but this is something that we have to live with. So actually, the ideas that I have explained so far are easily applicable if you have an idea of what the reaction is that you would like to study. So in case of simple 2D potential energy surface, you might get an idea by computing the saddle points here, and then connect the two states by going through these saddle points. But there are many cases where the situation is much more complex, where you don't have a single saddle point that corresponds to the transition, and this is something that is not just not just create problems when you want to compute reaction rate constants, when you want to understand rare events. Whenever you have a complex system with many minima and maxima and saddle points, and you would like to compute the free energy as a function of a particular coordinate that you have chosen for physical reasons, then you might run into very similar problems. So it's not a surprise that many methods to overcome this problem have been developed. So we can distinguish here between methods that have been developed to compute free energies, where you need to sample rare regions in configuration space in order to compute free energies. And these include umbrella sampling, thermodynamic perturbation, metadynamics, adiabatic free energy dynamics, and then there are many methods to do that, and all of them have to address the problem of convincing the system to visit regions in configuration space where the system does not like to go by itself. And this is usually done with some kind of bias put into the system in one way or another, and then later the bias is removed by a proper reweighting. Now, you also have to bias your system in what I call the trajectory-based methods that I have discussed in part, and I'm going to discuss in a moment, like the reactive flux method, the Benegender that we have just discussed, where you really create trajectories. You may produce the initial conditions for these trajectories by blue moon sampling. Also here, you have to convince the system to go to some parts of configuration space where it actually does not like to go. You have to do something actually similar to also in the case of transition path sampling or milestoning. You have to induce the transitions that you want, but it turns out that you can do it in an unbiased way. And this is what I would like to spend the remaining part of my lecture about. So I'd like to mention that if you would like to learn a bit more on the history, at least of the early methods that are here on my list, and by the way, also the history of SICAM, then there is a nice book that came out recently by Giovanni Ciccotti and friends, basically a book about the first 30 years of computer simulation, and you learn about umbrella sampling, for instance, and you will learn why it is called that way. All right, so let me now switch to a particular method that I would like to explain, because I've been involved in developing it together with Peter Bohlhaus and Phil Geisler in the group of David Chandler more than 20 years ago, and that's transition path sampling. And you know what the nice part about transition path sampling is that the trajectories that you produce are unbiased. The way you find them is biased, but each individual trajectory is not. So the basic ideas that you follow here is that you write down an ensemble of all trajectories, so the probability of a particular trajectory to occur, and you then concentrate only on particular trajectories. For instance, on the trajectories that start in a particular state A and end up in another state B, or on trajectories we will see later that cross a particular interface in configuration space. Now, once you have written down such a probability density for pathways, you can sample the density with Monte Carlo methods, just like you sample a probability density in configuration space. In a regular Monte Carlo simulation where you take a particle, you move it to a new position, that's the red particle here, you find out, well, there is an overlap here, the energy is high, I should not accept, but then you try something else, and this is more convenient in terms of energy, and then the move is accepted. So if you follow the right acceptance rules, that then you will sample the equilibrium distribution. Now you can do something very similar in the space of trajectories. Imagine that you have a trajectory, you generate a new one following a certain procedure. Now, in transition path sampling, many such procedures have developed, but now for the purpose of this argument, imagine that you have some way to generate a new trajectory out of an old one, and then you accept to reject it. Now this one, the red one, is not so good because it's not reactive, so you reject it, but this one you could accept. So you repeat this many times, and then as a result, you produce all the trajectories, all the important trajectories that do what you want. And in this case, what we want is that the trajectories go from one side to the other. Sorry, now I have to repeat this. So let me just make one remark about why this works. Usually in Monte Carlo simulation, it is difficult to come up with moves that move more than one particle, but still lead to a decent acceptance probability. So what does that mean for pathways? If you transfer this to pathways, this means that you should only change parts of a pathway to have a chance to get accepted. But here we do much more. We change the entire pathway. How can this work? You know, the entire pathway lives in a very high dimensional space because the dimensionality of this path space is equal to the dimensionality of phase space times the number of time slices you consider in your pathway. So how can you get an acceptance probability here that is appreciably different from zero? The reason is that you produce the pathways using a rule that corresponds to the physical path probability. Then in the acceptance probability, you have lots of cancellations, And that's what actually makes transition path sampling possible, because you use the same rule to generate the path as the dynamics of the path, the dynamics requires you. Okay, so now imagine that you do this, then you can actually study rare transitions in all kinds of systems. I need to look at the time here. So let me just skip this example where we look at how a nanocrystal transforms from one structure to the next, and how the transition path sampling algorithm actually manages to find new mechanisms that you have not used as an initial pathway. Let me just briefly mention two other methods that are based on the sampling of trajectories, and one is transition interface sampling. This is a method that was put forward by Peter Bolhaus and Titus van Erp, and here the basic idea is to look at the states in a slightly different way. Instead of looking at the small states A and B, you look at what they call the overall states, written in these calligraphic letters A and B. And if you follow a trajectory, then you imagine that even if you leave the original state A, you still belong to the same overall state until you hit B for the first time. Once that happens, then the trajectory turns blue, and it remains blue until you go to A again. Now you can do this correlation, time correlation function formalism for these more general states, and you find out that you can, by doing the transition state approximation for these states, you find that you can write the transition rate constant in a very simple way. Why does the transition state approximation actually work in this case? It works because these two states, the calligraphic states, the overall states, are separated. So you don't see recrossings between these two states so easily, and that's why you can write then the transition rate constant in this way in terms of an effective positive flux. So this is the flux of trajectories coming directly from going into B, coming directly from A. Now, it turns out that you can compute this flux in an efficient way by introducing interfaces, and then for each interface you do a path sampling simulation where you allow only trajectories that cross these interface, and by looking at these trajectories you can compute the probability that a trajectory that has reached interface I also reaches the next interface, and by then concatenating these probabilities you get an expression for the rate constant. So this is an efficient way to compute rate constants in the transition path sampling formalism. Then there is another method that can be applied also for, that basically uses the same formalism, but can be applied for systems where you cannot go backward in time, because you don't know what the equilibrium, the stationary distribution is, and this method is the forward flux sampling method. Now let me just make let me show you some examples of how these methods have been applied. They have been applied to many different systems, but let's look now to a specific system, something that we have studied in my group in collaboration with Chantal Valayani and some other people in Spain. So what interested us was how cavitation occurs in water. Let's again look at the little movie, and what you see here in this movie is how ferns catapult spores in the environment. So if you look at on the underside of a fern leaf, you see these brown things, and if you look closer, you see that they consist of these containers that are filled with the spores. And of course, the fern has an interest to disperse the spores in the environment. And it does that by a mechanism based on cavitation. And here it is how it works. So what you see here is this kind of elastic beam that consists of many compartments that are filled with water. And under dry condition, the water evaporates, so you have less water in each compartment and reduces the pressure, and the pressure becomes negative. And at some point, the pressure is so negative that cavitation occurs, and the elastic beam snaps back. And after it has snapped back, you see here the compartments filled with the vapor bubbles. Now, how does this cavitation occur in liquid water at negative pressures? There are experiments that study this effect by isochoric cooling of water in little cavities in crystals. Here you see one of these cavities, and here you see the little vapor bubble. You can make this vapor bubble go away by heating up. Then when you cool the system again isochorically, so for constant volume of the cavity, at a certain point, the pressure in the sample in the liquid becomes so negative, becomes negative enough to produce a cavitation event. So how does this cavitation event happen, and why does it happen? Actually, why? The answer is also given by classical nucleation theory, because at negative pressures, the free energy for producing a little vapor bubble in the liquid has a surface term and a bulk term. So again, what results is a free energy profile that has a barrier. And so in order to go to the more stable state, which in this case would be the vapor state, the system has to cross this barrier, and this barrier prevents the cavitation from occurring immediately as you cross the coexistence line. In fact, you have to go far into the negative pressure regime in order to see a cavitation event, and this is how it happens. So the yellow spheres here just fill the cavity that forms. So you see that it is far from spherical. And this is a result of a TPS simulation. And you see that it grows, and at some point it goes over the transition state, the critical cluster, and then the system just flies apart. So we stop drawing the little yellow sphere. So if you look at the free energy of the system as a function of volume, you find something that actually follows the expectation of classical nucleation theory. In this case, classical nucleation theory almost gives you the quantitatively right result, provided you do the classical nucleation theory apply it in the right way. But what you see here is that the free energy has a barrier that decreases with more negative pressures, and also the critical nucleus that here roughly corresponds to the top of the free energy becomes smaller. So here you can, if you compute the rates, this is interesting because this is how you can make contact with the experiments. You find the strong dependence, of course, of the cavitation rate as a function of the pressure. And here you even find a cavitation pressure. So this is the pressure at which cavitation is observed with a certain probability in the volume that is studied in the experiment. Is quite close to the cavitation pressure that we determined in our simulations using a kind of Benegender method and also transition interface sampling. Now, let me mention a very new study. This is not something that we did, but something that comes out of the group of Peter Bohlhaus. I think this is a very impressive application of transition path sampling. What Peter and Arjun actually studied is the formation of methane clathrate in water under pressure. So provided that you have low temperatures and high enough pressures, methane in water likes to form these clathrates that consists of cages, and in each of these cages you have one methane molecule. Now there are different cages that can occur, and the nice thing that Peter and colleagues found out is that depending on conditions, the mechanism for this clathrate formation is different. It can either go through an amorphous nucleus or a crystalline nucleus, and at just the right condition, you can actually have both. You can have both mechanisms that compete with each other. Now, this is an impressive simulation because the trajectories, each trajectory from until these cages have formed, is about half a microsecond long, and you need many of them. So this is really quite a calculation. I just came out in PNAS, and there are some more articles on the way, I think. Okay, now the nice thing is that if you would like to do such calculations, now there are programs that you can use to do that. Let me, perhaps I have some time left. Perhaps I can tell you a little bit about, I think, a problem that is a problem that goes beyond path sampling simulations, and that this is also a problem that cannot be solved just by throwing more computing power at it. And this is the problem of understanding. I think in many fields of computational science, now the problem is not generating data, but understanding them. So this is, I guess, what Eugene Wigner meant when he said, it's nice to know that the computer understands the problem, but I would like to understand it too. And he said it apparently commenting on the results of a quantum chemistry calculation. So let me explain what I mean in the context of path sampling when I say we would like to understand. What we would like to have is in a complex system, a low-dimensional model of the process that interests us. A low-dimensional model expressed in terms of some collective variables, let's call them Q and Q prime, that carry a physical meaning. If we are able to get that, and we can then show that this low-dimensional model produces the results that are compatible with the experiment, then we say we have obtained some understanding. Now imagine that you have a potential energy surface like this one with a saddle point here, and you look at this as a function of Q and Q prime, but you only consider Q first. Now in the two-stable state, this is, by the way, a slide that I made for a talk that I gave in Italy. In the stable states, the value Q has values that are here or here in the green or in the red part. So you would think that perhaps looking at Q suffices in order to understand what's going on. But the problem is that you have the saddle point that you have here lies completely in A, and there are configurations in A that, if you let them go, always go to B, because they are in fact already beyond the transition state, which you don't realize if you look at Q only. The situation is a bit like that. You know, I'm actually a mountain boy, so lots of cows around. Now imagine you have this situation. You have a cow and a fence, and there is not just a cow, there is also a fly. You know, where there is a cow, there are always flies. And now this is a system that has two states. You have the cow that can exist left of the fence or on the right-hand side of the fence. Now, if you take the cow and move it over to the other side, the fly will follow. So if you just look at the fly, you will think, wow, this is a good reaction coordinate, because, you know, the fly is either on one side or on the other side. But if you try to move the cow by moving the fly, the cow doesn't care. So the cow is the coordinate, the fly is the coordinate q. In order to move the system from one side to the next, you have to also move the cow, because if you just move the fly will just fly back to the cow. So this is the cow. The reaction coordinate. So, well, a more quantitative way to look at it is in terms of the committer, and the committer is just, a measure for how committed a certain configuration R is to, let's say, the stable state B. It quantifies the probability that if you start a trajectory here, it will always go to B. So this is a quantity that is very central to the transition path theory of Erik van den Einde. It also has been used for a long time in different fields. Is also known as p-fold, or the splitting probability. If a configuration has a committer of 1/2, then you say this is a transition state. And by analyzing reaction coordinates in terms of committers, you can find out whether they are good or not. What you require from a good reaction coordinate is that it parameterizes the committer. The committer is something that tells you what's likely to happen next. And this is exactly what you would like a reaction coordinate to do. You would like a reaction coordinate to tell you how far along a transition from A to B, let's say, you have already proceeded. Now, if Q is able to tell you what the committer is, then this is exactly what you expect from a good reaction coordinate. You can test reaction coordinates by looking at committer distributions. In the case of a good reaction coordinate, if you look only at configurations that are here along a particular value of Q star, they will all have the same value. But if the reaction coordinate is not so good, then you will here sample configurations that either go to A or to B, and you will get a committer distribution with 2 peaks instead of 1, which means that this relation is not obeyed. It's not so good for a reaction coordinate. Finding reaction coordinates is not so easy. Here's an example where we tried hard but didn't really make much progress. We looked at how a gold nanoparticle freezes. If you compute the free energy as a function of the size of the crystalline nucleus, you find that it has nice minima. And then you can ask, how does the system go from one minimum to the other one, and try to find coordinates that describe that. In fact, in this case, we looked at many coordinates and we did not really find a good solution, even though we tried, we also used a method that is called likelihood maximization. This is a beautiful approach that was invented by Baron Peters and Bernard Trout. What they envisioned was that you can use the fate of trajectories that you start from configurations to improve a model for a reaction coordinate. So this is a way to find a good model that to basically find reaction coordinates, and the idea is that you look for that reaction coordinate that maximizes the probability of the events that you have observed. Try to apply this method that in many cases produced nice results. In our case here, it did not. So I think this happens quite frequently if you study rare events, that you are able to generate them, but then when you try to rationalize them in terms of a few reaction coordinates, it turns out to be hard. And here I think that, and you don't need to be a visionary to say that, I think that machine learning actually offers us ways to solve this problem, ways to find reaction coordinates that carry the essential physics of the transition that you would like to study. There is, of course, a hype now going on about machine learning, but I strongly believe that machine learning is here to stay, and it is here to stay because it works. And I think it will, and it is already transforming the way in which we do science. And this will happen also in the field of molecular simulation. Is already happening in the field of molecular simulation. Think about the machine learning methods that are used to encode potential energy surfaces. But there are many more applications of machine learning methods. Coming up with low-dimensional representations, for instance, by using autoencoders. That's just one example, or using neural networks to detect structures like Jutta Vogel and Mark Duckerman did, and then use these neural network detection methods for local structures to construct path collective variables, and then use those to enhance the sampling. So these are just two examples of things that you can do. I also like this approach here proposed by Gerhard Humer and his group, where they used machine learning methods. In particular, they used the neural network to learn the committer, and then use the committer to bias the selection of shooting points, and then use the new shooting points to improve the model they have for the reaction coordinate in a reinforcement like scheme. And then you let the system go, and it will. And this way of doing things based on machine learning will improve the sampling that you do. So I think machine learning has lots to offer, and I expect to hear something about that in the talks that follow mine, that it can help us in constructing models, in constructing potential energy surface, that it can help us in finding reaction coordinates, that it can help us to improve the sampling. Maybe at some point it will even write the papers for us. This is something that I recently saw, that they used machine learning to write a book. I have not read the book though, but I hope this is not the future, but the future certainly is that we will use a lot of machine learning also in the area of rare event sampling and its applications. Thank you.
Okay, thank you very much, Christoph, for this very thorough and illuminating presentation. Sorry. Now we move to the discussion section. As I mentioned at the beginning, you can, if you want to ask a question, you have the Q&A panel in your window, and it's enough if you indicate, I want to ask a question, so then we can have the list of people who are interested in asking questions, and then those who have asked a question, you will receive a message in due time indicating that you should unmute yourself. Then I will introduce the name of the list of people who want to ask a question, and then you can ask it directly to Christoph. So far we have already 3 people who have indicated the interest to ask a question. So the first one is Mark Tuckerman. I will not read again the text. Maybe you can explain that for everybody.
So Mark will ask it. Okay.
Yes.
Yeah, I typed the question in, which I realized I wasn't supposed to do. Sorry, guys, about that. I'm supposed to just say what the question is. So first of all, Christoph, that was really, really nice. I thoroughly enjoyed the talk. I did just want to come back to this one point that you made about the uniqueness of the free energy. So, of course, when you choose to express the free energy in a different coordinate, like you showed, that was the example that you had. This 2 state goes to a kind of 1 state when you introduce a certain kind of transformation, and you showed what that would be in this case. That is exactly the same. It's exactly the same free energy. all you've done is you've warped the space, right? So of course you have to look at it in that different space, but that new one state distribution or profile that you showed is exactly correct in that space. And so you haven't done anything mathematically, and therefore you haven't actually changed the free energy. So I'm not sure that's the argument you want to make for uniqueness, right? The argument.
I agree. So all the transformation does is to compress certain parts and expand others, and that then looks like leads to a shape that looks different. Although it's the same set of configurations that you have.
Yeah.
Right.
And you can always map back to get the and if you do, you will get the correct free energy. And, in fact,
both of them are correct, right?
Yeah. And in fact, this could be a good way to develop an enhanced sampling method. It's a little like, okay, we did this some years ago, but this is also kind of in the direction that Frank Noe was going, right, with his machine learning approach, where you can try to learn a transformation that knows something about your free energy and tries to compress these barriers, right?
Absolutely.
Yeah.
Absolutely.
Okay. Thanks.
Thank you
very much. So next person is Manuel Corral, also, who wants to ask a question. Please, Manuel.
Hello, and thank you very much for your talk. Very interesting, and thank you to the organizers for the event. Very nice initiative.
So
I'm afraid that mine is a very naive question, because I work in the field of quantum simulations. And when you talk about transition sampling events, the transition sampling ensemble, sorry. But the first thing that came into my mind is sampling a reaction coordinate is tough enough. How do you manage to sample many in an efficient way? But I think you already talked a little bit about that at the end of your talk.
Yeah, I mean,
thank you.
That's of course true. So if you want to, I think in many cases, if you want to learn about a particular process, you need many examples of trajectories, and producing them is costly. And sometimes it's so costly that you cannot do it. So you cannot. But then in other cases, you can. And with the progress of computers, and I mean, just look at these simulations that Peter recently did on GPUs. This is really impressive. So these are simulations that I guess could not have been done a couple of years ago. Now they can do them because they have the software tools to do it, and also the hardware that you need. But certainly, I mean, these are simulations that really are at the edge what's possible. But now soon we will have the exascale computers, and they will solve all the problems that we have.
Okay.
You're very optimistic. So thank you. So, we'll see. So next question is by Rohit Goswami.
Yeah, hi. First of all, thanks so much for the talk. And I just wanted to point out that, like, I'm not really sure, especially with the examples shown, like of neural networks, which use many features, but then give out aggregated features. They may not have, I mean, they're very difficult to get a physical interpretation out of. Yes. So yeah, I mean, I'm not really sure if that's always desirable.
Yeah, I mean, that's certainly a point. Maybe I was too optimistic about it, but this is certainly a difficult point that you mentioned here. In some cases, you don't care, right? If you think about encoding a potential energy surface, the only thing that you want is that it works. If you want to, and you don't you don't need to understand how. In other cases, you would like to understand how, and then more work, of course, needs to be done. If you want to use your machine learning procedure to improve your sampling, also in that case, what you care about is that you sample faster. In that case, I don't think that's such a problem. But if you use your machine learning to produce collective coordinates that you then use to create a simple model, then this is a real problem, and I don't really know how to solve it, because then you don't have the simplicity that allows you to really understand. But I agree with you that this is something that this is a problem.
Thank you for the clarification.
Thank you. So the next person is George Trenins, also.
Hello. Thank you very much, Professor Lagerton, for an excellent talk. And I have also, like Manuel, been working with quantum stuff for the last many years, and many of the methods here are new to me, so I apologize if my question is based on a misunderstanding. I was very intrigued by the transition interface sampling method, and on your slide, there was an equality between the rate of the transition and a bunch of static thermal averages. And you said that there isn't the problem of recrossing because the states A and B, the not calligraphic states A and B, they are separated in space. And I was wondering, so in principle, if one imagines the limit where the you choose one of the states in a silly way, so the state A is the complement of state B, then you're back to the Benegender approach and the reaction something. So the problem is back. So how does one?
No, so this wasn't correct what I said. I think so. The overall regions are in fact adjacent, but right. the recrossings are avoided by the definition of this overall state. It's if you want to have a recrossing, then the system has to go all the way back to the original state. Then you would have you would have a recrossing if this happens in a correlated way. But since the original regions A and B, since they are separated, this is unlikely to happen, to play a role. I don't know if I explained it in a way that is understandable.
No, I think it's shed some light on it for me. Thank you very much.
So there is a reminder that we have then the gather session. We can continue. There are these even whiteboards. So you want to have a more technical discussion to clarify it. So next question is by Michele Ceriotti. Hello, Michele? No? Okay, so maybe he's not, I don't know if I have a problem with the sound. Maybe we can move to the next question by Giancarlo Francese.
Yes, hi. Christoph, very nice talk, thank you. I'd like to ask you if there is any work about this right definition of the reaction coordinates that you were discussing at the end, for example, by using the committer or the likelihood method for simple phase transitions where we know which one is the order parameter. For example, if we take a fluid phase transition, like for example liquid gas, but also liquid. There is no symmetry. You know, at the end we have to combine energy and density, for example, to get the right order parameters. But there are other ways in which that's not very clear how to combine it. The prefactor you have to use, because it's just a matter of how do you project your free energy on the coordinates as you were showing, you know, the different way of looking at the same free energy by different perspectives, basically. So is there any work done in this direction to show that by using the committer you can really define the right order parameters for a phase transition, in which it is not clear which one is the, you know.
You mean there is a systematic procedure to arrive at a reaction coordinate that parameterizes the committer, or I'm not sure if I completely understand your question.
Okay, so maybe we can have a little longer discussion later if you like. But anyway, it is just, you know, the simple question is if there is any work done in this direction already, not just, you know, as example, but as an effective way to show that it works in more complicated situations.
The papers that I know are all about, you know, what people mostly do is to propose reaction coordinates and then test whether they are good, or construct new ones out of a set of given reaction coordinates, for instance, by combining them linearly, and this is often done with likelihood maximization.
Yeah. Okay. So I will definitely.
But I am not aware of any. That would be very interesting if you have a procedure that
we can discuss it. It's definitely
produces a reaction coordinate automatically out of some information about committers.
Yeah. Yeah. Let's discuss it. Thank you. Thank you very much.
Yeah. Thank you. So we don't have much time left, but maybe you can still consider a couple of questions. So the next one is by Peter Bolhaus.
Yeah, Peter Bolhaus here. So thanks, Christoph, for a very beautiful overview. I recognized a lot of slides and concepts. It's very nice to see everything in place. I had a question. I mean, for you showed biomolecular systems in the beginning. And as we probably all know, there's a whole field of researchers doing Markov state modeling of these type of processes for rearrangement in biomolecular systems. And there also short trajectories are often used. So this sounds very adjacent to the whole idea of path sampling. So can you comment on what the relation is between Markov state modeling and TPS?
Well, you probably know that much better than me. So to me, the problem is in generating these trajectories, right? What you do in transition path sampling, as you know, is to maintain some condition at all times, and you don't have to wait for the reactivity, and you don't have to wait for it to occur spontaneously. So I see the Markov state model as a very good tool to analyze, let's say, a very long molecular dynamics trajectory, but it does not really help you in overcoming high barriers that you might have.
Mm-hmm. Okay.
So do you agree about that?
Yeah, I mean, I think you're right, but I mean, the follow-up question is if the MSM construction can be used as a proxy for the stable state definition that you have, you have not mentioned very much about how to define these stable states. Right. But in complex systems, it's actually quite difficult to define the stable states. And there's an old idea that was proposed by Vijay Pandey many years ago that MSMs can also be used as stable state definition for TPS. And I think that is still something that is underdeveloped. And I think it's a very nice way to marry these two methods.
Yes, this is something I have completely swept under the carpet.
Yeah, perfect. Yeah, that's for later discussion. Yes. So maybe we can try to fit two last questions if they are not too long. So one is by Fabio Pietrucci.
So thank you, Christoph, for your talk. It was really, really nice. And I think it should be mandatory for young students and people approaching this kind of simulations to follow your talk. So I have a question about the cow and fly system, which I think it's really a brilliant way to explain the problem. And I think there is something deep into this example. I don't know, or maybe I'm just stupid, but the point is, I think when we have a transition between metastable states in a very complex phase space, including many degrees of freedom and so on, and we discuss about the difficulty in finding reaction coordinates, exactly with the example of the fly and the cow. I think we have maybe a problem in understanding causality in physics. So what is the cause and what is the effect? Because in the end, a reaction coordinate tries to capture the cause of a transition. So like a trigger that is necessary to pull to make the transition happen. And then there are many effects, which are side effects, like the fly going around. And of course, you can parameterize also this, you can use this, but they do not work, right? So is it something about the very definition of cause and effect in this field?
Yeah, so this is an interesting question, but I think one way to look at it is to view the reaction coordinate as a handle. So if you take that reaction coordinate and pull it, will the system do what you want? Right? So in a sense, it is the coordinate that allows you to cause a transition, if you want to use these terms. Which the fly does not, but the cow does. So the cow is the direction basically in this cow-fly system in which you have to push.
Yeah, that's why I think it would be nice to have a definition of cause and effect in a process, in a phase space where you go from one metastable state to the other. But I don't know anything. I don't know any attempt to do this, and that, I think this is really a problem when you try to find the reaction coordinate.
Okay.
It's really the difference between causality and correlation, I think.
Okay, so I think that calls for also discussion afterwards. Maybe we can move to the last question. Actually, Baron Peters has had two questions. I don't know if you can combine it in one.
Yes.
And then just the last one.
I will combine the other one.
One of them was a foolish accident of me trying to type notes for myself. And so please ignore the second thing. I just wanted to follow up on the point that was raised by Tuckerman, and I think that this will be obvious to both Mark and Christoph and maybe many in the audience, but it is true that results from some reaction coordinates are interconvertible with others. So, you know, the example that Christoph showed nicely illustrates this. He showed nucleus free energy versus volume. You could equally plot that nucleus free energy versus radius, and the two results would be related by this 4 pi r squared Jacobian, and you can interconvert those. But you might, and this is kind of related to Francis's question as well, you might also try to use the order parameter of density, right? And that would work fine at the macroscopic scale if you want to compare the two macroscopic phases, but it does not capture the same isosurfaces that will detect differences between large scale density fluctuations and the localized creation of a little bubble. So those cannot be interconverted because they slice the phase space differently. And so, you know, I completely agree that in many cases we can interconvert these results, but also there are really subtle choices like that where you find that there are differences.
I mean,
information
I
lost.
not want to imply that you can interconvert any free energy, right? But just as an example of a very simple case where you can do it and you get different free energy profiles, and you have to be aware of that.
Yeah.
But certainly, if you're looking at if you look at a completely different coordinate.
So I know that this is completely obvious to many of the other people who do this all the time, but for the students in the audience, you can't always take somebody's free energy profiles and add a Jacobian and get back your own. It doesn't always work that way.
Okay, thank you very much. I think when we are having a very interesting and open discussion, I think that's the purpose of these sessions. But I think that we should move on to the next talk because we are already somehow delayed. And I hope then you can also benefit from the gather session afterwards to continue some of these discussions more informally. So we will move now to the, as I said at the beginning, there are 3 talks, and then there are now 2 by younger researchers than the previous lecturer. And the first one will be by Luigi Bonatti. He's doing his PhD in ETH Zurich, and he will be talking about training collective variables for enhanced sampling via neural networks. So it already touches some of the points raised by Christoph. So please, Luigi, now the floor is yours.
Thank you very much. Okay, thank you very much for the introduction and also for giving this opportunity to present my work today. It's really an honor for me. And in this talk, I'm gonna talk about using machine learning methods to derive collective variables for enhanced sampling simulations. So as we have heard just moments ago from the previous talk, atomistic simulations are often limited by kinetic bottlenecks, which arise due to the presence of high free energy barriers between metastable states. And in order to extend the scope of molecular dynamics simulations, several enhanced sampling methods have been devised. And I will focus here on a class of methods which are based on the identification of collective variables, a small set of collective variables, which should be related to the slow process to the slowest relaxation mode of the system. Once they are identified, one can add the bias potential to these collective variables, and this results in enhancing the fluctuation of the selected CVs by lowering the corresponding free energy barriers, thus escaping from the local minima. Or in a different perspective, we can say the effect of this external bias potential is to modify the sample distribution in order to increase the probability of having a transition from one state to the other. Among the methods which are based on collective variables, we can name, for instance, umbrella sampling, metadynamics, and also a recent method which is called on-the-fly probability enhanced sampling, and it's closely related to metadynamics. So the question is, how do we choose appropriate corrective variables? Because the success of this procedure critically depends on the identification of an appropriate set of collective variables. Here we can see a typical free energy landscape, which is composed by several metastable states and multiple kinetic pathways connecting each other. So in general, how do we choose collective variables? So in principle, we know how they should look like. For instance, they should be able to drive the system from along the free energy pathway connecting the metastable states. Or in other terms, they should be related to the processes which have slowest relaxation with the longest relaxation timescales. Because again, the isocommuter surfaces are known to be the ideal definition of a reaction coordinate. However, more often than not, we do not have any of this information at the beginning. So we can try to derive once we have converged simulations, but in the practice, when we want to study a new system, the identification of CVs often rely heavily on physical intuition and trial and error. Here we take a different perspective. So we don't want to find the best collective variable. Rather, we want to make the best guess out of the limited information which is represented by the knowledge of the metastable states alone. Indeed, we can look at the free energy landscape as composed by islands of metastability in a sea of very improbable configurations. And the question is, what can we do when only the metastable states are known? This is a situation that occurs often in the practice. They could be, for instance, the reactant and product state of a chemical reaction, the liquid and solid phase, the folded and unfolded state of a protein, and so on and so forth. The simplest idea is to enhance the sampling in the direction that maximally separates the two states. And actually, there is a statistical analysis technique, which is called linear discriminant analysis, which does exactly this task. And this has been applied also successfully, I would say, to enhance sampling by combining a small set of descriptors into collective variables. And here we want to build on the same idea and try to design even better CVs, given only the metastable states. In order to do so, we start by reviewing briefly how LDA, linear discriminant analysis, works. It searches for a linear projection of a set of input features such that the classes are maximally separated. So in our case, the classes are the metastable states, and which we characterize with a set of physical descriptors D, which could be, for instance, distances, angles, dihedrals, coordination numbers, but also more complex quantities. And we run short-term standard molecular dynamics simulation in the basins, and we compute the values of these descriptors. Then we can compute the mean values of the descriptors and their covariance matrices. And with these quantities, we can define the so-called within scatter matrix, which is related to the intra-basins fluctuations, and the between scatter matrix, which is instead associated with fluctuations between the different states. And Fisher criterion states that if we want to find the optimal direction, so the direction in which the states are maximally separated, we need to maximize the ratio of the between scatter matrix and the within scatter matrix in the projected space. And in the practice, we can solve this as a generalized eigenvalue problem, where the eigenvalue V measures the amount of separation along the corresponding eigenvector. And once this direction is found, we can use this as a collective variable by projecting the descriptors along this direction. And this is a robust approach, but it suffers from several limitations. The most important one being the fact that it can only provide a linear combination of input descriptors. And also typically the number of inputs that can be handled is quite small. So here we want to lift this limitation by combining with neural networks. This can be seen as a nonlinear LDA extension. And this is achieved by optimizing a neural network using the Fisher criterion as a loss function. How does it work? The inputs of the neural network are a set of a possibly large set of descriptors, which are given to a neural network, which, thanks to the composition of several linear and nonlinear functions, is able to learn linearly separable latent features. And on the topmost hidden layer, so in the latent, we learn a few latent variables in which we apply LDA. And by measuring the eigenvalue and using it as a loss function, namely by maximizing the eigenvalue of the generalized eigenvalue equation, we can increase the discriminative power of the neural network. Finally, once this procedure when the training is done, we can use this as a collective variable to enhance the sampling. This is just a toy model to illustrate the difference between the linear version and the neural network one. So here we have two states represented by points, and the lines here represent the isolines of the CV, which of course in the case of LDA are linear, while in the case of the LDA, they connect the two basins in a nonlinear way. And thanks to the nonlinearity, as we can see in the inset, the neural network version is able to discriminate and to separate much better the two states. So before proceeding to the applications, I would like to briefly describe the steps that need to be done in order to train and to use this CV. So first, we said we need to run short molecular dynamics trajectories in the metastable states and compute the descriptors. with this data, we can train a neural network to maximize the LDA objective function. We use the PyTorch machine learning library, and if you want to try it out, there is a I also released a Google Colab tutorial with which you can use it to train it. And finally, we can use this as a collective variable to enhance the sampling, and by importing this variable in plumed. And just to show the ease of use of this method, we just need here there is a plumed input example in which you just need to complete descriptors. We can import. I developed a plumed interface to load PyTorch models trained in Python, and then we can choose the bias potential of choice. It could be either metadynamics, umbrella sampling, or OPES, and so on. So the first example is actually a benchmark, which is alanine dipeptide, which is a small peptide that is often used as a benchmark for enhanced sampling simulations. And as we can see here in the picture, it is characterized by two metastable states, which are well described by the two dihedral angles phi and psi, which form an almost ideal set of CVs. However, since we want here to proceed in a blind way, we do not give any information about dihedral angles. Rather, we build our descriptor sets out of the interatomic distances, and so between heavy atoms. And we run with the data collected from unbiased simulations. We train our CV. We use it to enhance the sampling. And actually, it's the sampling efficiency. It's similar to the reference one, in which phi and psi are used as to define the bias potential. However, here I want to focus instead to something else, which is also related to what Professor Delago was saying before about interpretability of machine learning models. So here, in order to try to understand how the CV works, we computed the isolines of the CV in a physical space, which is the one of the phi psi angles. And on the background, the free energy surface of the system as a function of these two angles is reported in the background. And it's interesting to see how the deep LDA CV connects the two basins in a nonlinear way, and also how that there is and also we can see that the direction along which the system is driven when applying the bias along this CV, it's quite close to the free energy pathway which connects the two basins. And this is something which we did not expect, because in the first place, because we did not give any information but for the metastable states to the CV. The second example is an intermolecular aldol reaction, which involves the formation. I mean, the transition mechanism involves the formation of a carbon-carbon bond together with a simultaneous proton transfer between the oxygen. And as before, we use all the distances between atoms to build our descriptor set. However, here we transform them into smooth contact functions in order to have, I call them here, chemically informed descriptors. What I mean is descriptors that can more easily recognize the presence of bonds in the system, which is what we are interested in when we're studying chemical reactions. And as before, we train our CV on the reactant and product state of this reaction, and then we use it in combination with OPES to enhance the sampling. And as you can see, this allowed to observe several transitions between one state and the other. And this diffusive behavior implies that the CV is able somehow to capture the concerted mechanism, even though, once again, no information was given about the transition. And this diffusive behavior allows us to accurately estimate the free energy profile along all the reaction pathway. And this is the free energy profile along the deep LDA CV is reported. And trying to address the call for physical understanding about machine learning model, here we try to do something in this direction, which is we rank the features, we rank the descriptors based on the contributions of based on their contribution to the CV. And this could be useful both to highlight which are the features that the machine learning model thinks they are relevant, and also to obtain insights about the process in case of complex systems. And we did this, we tried a couple of approaches. The first was just to consider the magnitude of the weights between an input feature DI and the first layer, and then taking also into account the standard deviation of the input. And the second one was, which is more robust, it's based on the derivatives of the collective variable with respect to input descriptors. And this is computed for every point of the training set, and then it's averaged. And in the case of the relatively small neural network employed here, we found these two methods to provide very similar results. And indeed, both methods highlight the presence of three dominant descriptors, which, as you can see in the inset, are the carbon-carbon distance and the distances between oxygen and the hydrogen, which are involved in the reaction. The last example is an application to ligand binding. We applied between the calixarin host and 6 different ligands taken from the 5 sample challenge. And here we want to enhance binding, unbinding events to compute absolute binding free energies. So our reference state here are the bounds, the state in which the ligand is within the pocket, and the unbound state. In this challenge, the binding pose was known. And here we wanted to use the deep LDA CV to include the effect of water into the collective variable set. And although this is important, because although water has long known to play an important role in the binding process, it's far from trivial to do it. Here we try to do it by using as descriptors water coordination numbers to describe the solvation both around the ligand and the host in a different way, separately. And in doing this and combining these water-based descriptors with deep LDA resulted in improving the sampling, and thus allowing to reduce the sampling error. Here you can see the ligand binding, the ligand binding free energies with respect to the experimental values, and the sampling uncertainty we obtain from our simulation with OPES are always smaller, for the free energies, are always smaller than 0.1 kilocal per mole. As before, we can try to understand something about the role of water also by looking at the descriptors contributions. And here we analyze separately the contribution of the descriptors in the bound state on the top and the unbound state in the bottom. And it's at variance with the previous example. We can notice how we have a contribution from almost every descriptor, but that this contribution can change quite significantly from one state to the other. And this can help us to understand something about the important fluctuations. For instance, in the bound state, we see that the most important contribution comes from this V4 descriptor, which measures the water at the proximity of the entrance of the binding pocket. While in the case of the unbound state, they gain a considerable weight, these V1 and V2 descriptors, which control the number of water molecules inside the pocket. And this is very important because in order for the ligand to correctly bind inside the pocket, there need to happen fluctuation towards the dry state of the cavity, so with no water inside. And being able to enhance these fluctuations is key to improving in an efficient way the sampling. So we can see that in this case, I mean, LDA is able to, deep LDA is able to describe this collective motion of water that is able in turn to promoting binding and unbinding events. To conclude, we said that we showed that by combining Fisher discriminant analysis and neural network, we can design our initial guess, we could say, our guess CV from equilibrium fluctuations. In particular, this is achieved by using neural networks to compress a large number, possibly large, it depends. In this case, it was relatively small, but a large number of descriptors into CVs. And it's a general procedure. It can be used with any collective variable-based method. And it resulted in efficient sampling of different kind of rare events, from chemical reactions, ligand binding, and also very recently it has been applied to crystallization processes. There is this preprint just came out on arXiv a few days ago. And finally, the deep LDA descriptors, the analysis of the importance of the descriptors can be used to identify the relevant features as well as filtering them, which I think it's an important property in order to apply it to complex system where you don't want to apply your bias potential to every degree of freedom of the system, of course. And finally, I would like to conclude by thanking my supervisor, Professor Michele Parinello, as well as Valerio Rizzi, with whom I collaborate with this work, and the whole Parinello group, and thank you for the attention.
Okay, Luigi, thank you very much for this nice presentation. We have now a bit of time for questions. I remind you that those of you who want to ask a question, you simply should indicate in the Q&A panel that you have in your window in Zoom that you want to ask a question, and then you will receive a note from the support team indicating that you have to unmute yourself before asking the question. In that way, this is more interactive than just writing it down. So the first question is by Rangsiman Ketkau.
Yes, can you hear me?
Yes.
Yes, thank you for your wonderful talk. So yeah, it's very interesting that you try to combine the neural network and the enhanced sampling technique together. So my question is very simple. In order to train the model, you have to run the general MD simulations to generate the trajectory of the reactant and the product states beforehand, right? And then you run the model on that trajectories. So how do you convince the people to use your method? Because so if you have to generate or run the reactant and the product, so why don't we just use the more straightforward or simple CV rather than your CV? Like for example, general chemical reaction, for example, the addition reaction, you can just use the distances between the carbon atoms as a CV, right? So yeah, for a simple reaction, it's good to use that CV, but would it be like time consuming to train the model for describing a simple reaction? Like, do you get what I mean?
Yeah, thank you for the question.
Yeah.
So what we wanted to show here was the fact that we can, of course, if we know, I mean, if it's a simple reaction and we know which is the slow, degrees of freedom, we can try, but often in complex example this doesn't work. For instance, here in the Aldo reaction, there were already 3 different descriptors. So the carbon-carbon, which from physical or chemical point of view, I would have thought to be interesting. How do we combine them? Of course, this is a simple example, but we showed that in an absolutely blind way so without telling anything about the important distances and the important descriptors, we can derive a CV which effectively promotes the sampling from one state to the other.
Okay, thank you. I do have another small additional question. So, what about the transferability of your model?
Transferability.
Yeah. What do you mean? I mean, the idea is in this case.
So it means that for using your method, we have to train the model every time we want to explore the new reactions, right?
Yeah, yeah, exactly. And this it's not transferable basically at this stage. The point is training here. The training part really takes a small, minimal computational time, because for instance, in the case we run unbiased trajectories for a few picoseconds, and we just run unbiased simulation for a few picoseconds. We train the CV, which is in the case considered here, we're very, very quick and cheap from the computational point of view. And then the bottleneck is always the non-sampling part, in which we need to run for hundreds of picoseconds, nanoseconds in order to get converged simulations, while the training requires just a few picoseconds. So it's order of magnitude faster.
Okay.
Yeah, I mean,
thank you.
That's something which, of course, it would be nice to have in the future. So to have something which is more transferable.
Okay, thank you very much. So there is another question by Mark Tuckerman.
So Luigi, that was a very, very nice talk. Thank you. Work coming out of the Paranella group is always fun to follow. So you present this as kind of the traditional picture where I have a state A and I have a state B and I have some transition state between them. But of course, many landscapes are not like that, right? You may have a number of different basins that you're interested in, and you want to explore pathways that go between these different basins where you may have many transition states. Now, what I'm wondering is how easily could you extend this approach to that type of situation? In other words, can you do it in one shot where you handle all the basins at once? Or would you have to go sort of pairwise between these different basins, in which case it seems like the approach would generate some sort of piecewise collective variable that might not be the same for each transition.
Yeah.
Unlike what you would want, right? Which would be one that is, kind of uniform or continuous.
Yeah, enough. Thanks. Thank you for the very interesting question. So actually, here in the case of deep LDA, we only apply to the case of 2 states, while in the linear case has been applied also to multi-state scenarios. And actually, the LDA techniques as the LDA method as a general formulation for more than 2 states. And in general, what you obtain is that if you have C classes, you obtain with LDA C minus 1 collective variables or direct projections. So it's straightforward to generalize to multiple states. And it has been done, if I remember correctly, in the case of a chemical reaction with 3 different metastable states, just by applying LDA, the harmonic version. So.
Thank you very much. So there is a next question by Alessandro Laio.
Hi, this is Alessandro Laio speaking. Thanks very much for this great talk, very, very interesting under many, many points of view. Well, actually, I have a pretty general question, which is a little bit related with my personal experience. So now my personal experience, finding a collective variable which separates nicely reactants and products is not so difficult. So is something which, with a little bit of chemical intuition or physical intuition, one very often finds a good one or many good ones which separates reactants and products. But so now what your work seems to indicate that if you try to do a nonlinear transformation to your initial coordinates, which really try to make reactants and product as far as possible, then what you're going to get is something which looks like the minimal energy path or the minimal free energy path, or the committer or whatever you like. No, so this thing is a very, very strong statement somehow, no? Which in a way, did you try to make this thing a little bit more quantitative? Did you try, for example, because okay, clearly it's very, very clear that in special cases this happens to be the case, and you have shown some examples. No, but do you think it exists some formal reason why this can be the case?
Thank you for your really interesting question. So first of all, I mean, I would like to, the purpose of this CV, as I said at the beginning, was not exactly to find the ideal CV, the ideal reaction coordinate. Rather, it all started from the idea to say, okay, but more often than not, what's our starting point when studying a new system? We know, not always, but often we know which are the reactant and the products, or the state A, state B. What can we do from that? In the process, we discovered quite surprisingly, I will say also, to answer your question, that this nonlinear transformation was actually, in some cases, very good. And also, I didn't show it, but for some other work I'm doing, I was computing also the committer to check after the simulation the quality of the CV, and in some cases it's very good. So is there any formal reason? I don't know. The point is here it's very difficult just to relate equilibrium fluctuations with transition.
Yeah, actually, I had in mind some simple formal argument, for example, related with the recrossing frequency or something like that, that you do a deformation and you make, well, I don't know. Well, here it's just a suggestion for a possible.
No, that's very.
It will not be true in general, but maybe it's possible to think in this direction, no?
Yeah. I think the difficulty here in applying also the difficulty here is to identify the in a formal way what you want your machine learning model to do, because of course, especially if we do not have information about transitions, it's very difficult to learn an optimal CV. And in this sense, I think it cannot be seen as a solution for every problem. Rather, I think an interesting possibility is to use as a first guess to collect some transitions, eventually maybe also discovering new states, and use this data to design better collective variables.
Okay, thank you very much.
Thank you for your suggestion.
So we are running a bit late, but maybe there are like 2 questions if they are short before we move to the last presentation. One is by Rohit Goswami.
Yeah, thank you. So sorry if this is a bit technical, or you can just let me know, but like I was wondering, what is the complexity of the input descriptors used? Is it just like raw distances or like Z matrices, Coulomb matrices? And also, was there like dropout used, or how does the architecture of your neural network change the results? Or yeah.
Short answer. I mean, then we can maybe also talk afterwards the gather session. However, they were quite simple, so they were just distances or coordination numbers. So let's say contacts, so function of distances. And since the neural network was a simple feed-forward one, and the choice of the parameters was quite robust. I mean, also the sampling was quite robust with respect to the choice of the parameters. And but I can show you also some results afterwards if you want.
Yeah, sure, that would be great. Thanks a lot.
Thank you. I mean, it turns out that the last person who wanted to ask questions said that it was already been answered. So I think we can move to the last speaker. I forgot to mention earlier that these 2 talks have been selected from all the attendees who send us a request to present a poster. And therefore, in particular, it means that both Luigi and Janjan's posters are still part of the session. So you can visit their posters afterwards in the gather session. And indeed, some of these discussions, questions that you have may keep on going in the second part of the event. So thank you again, Luigi. I will then move to the last talk of this first part of today's event, and that will be given by Yanyan Liang, who is doing his PhD at the ICAM, Institute of Computer Interdisciplinary Center for Advanced Material Simulations in Bochum in Germany. And she will be talking about the identification of multidimensional reaction coordinates for crystal nucleation. So Yanyan, now the floor is yours.
Okay, let me just try. I think you can see the laser pointer, right? So yes. So hello everyone, I'm Yanyan Liang and I'm a PhD student at ICAM's Ruhr University Bochum. So today I want to present you our research on the identification of a multidimensional reaction coordinate for crystal nucleation in nickel 3 aluminum. So we are particularly interested in this system. That's because actually this is a basic component in high temperature nickel-based superalloys. And also this bimetallic system really has a very complex phase diagram. So for example, if you look at the equilibrium phase diagram here at 75% nickel composition, actually it predicts that it has a stable phase, that is the chemically ordered L12 phase that can be stable up to the melting temperature. So for crystal nucleation in nickel 3 aluminum, we really want to understand what is the underlying atomistic mechanism for these bimetallics, because actually there are not so many studies focusing on the atomistic insight from the for the bimetallic alloys. And then compared to the pure system, actually the complexity in the multi-component system will increases a lot, since there are interactions of different chemical elements there. And then during the crystal nucleation process, there might be various crystalline polymorphs appear. And also there might be a change in the chemical composition and then the chemical ordering. So all of these factors will make the choice of the reaction coordinate rather difficult to really identify which degrees of freedom is important for the crystal nucleation in this process. So for the complex process of activated events, actually the true challenge really lies on finding the low dimensional descriptors to understand the underlying physics. So what people often do is to project the high dimensional phase space on some simple parameters or collective variables that represent the important degrees of freedom. So there is a really widely used theoretical model to describe the homogeneous nucleation of crystal that is called classical nucleation theory. It's already introduced in the first talk, actually. So one of the very key assumptions in the classical nucleation theory is they assume actually the crystal nucleation can be described by one-dimensional process that is solely depend on the radius of the spherical nucleus. But also, actually, people find out the crystal nucleation process, even in some simple model system, actually, it can be much more complex than the one-dimensional process, because it can appear as an ordering of multiple order parameters. So when it comes to the multi-component systems, it's even difficult to find the reaction coordinate, since I already said in the first part. So actually there might be change in the structure composition, and also there might be change in chemical composition, or also the potential chemical ordering and demixing. It might all play a role. So it's really challenging for us to find the optimum reaction coordinate to describe the complete crystallization process correctly. So since the identification of the reaction coordinate is really crucial in the description of the mechanism. And also we need to bear in mind that actually the collective variables that can distinguish between different states are not necessarily the good reaction coordinate. So it really depends on the potential energy surface we are looking at. So for example, if a process has a rather simple potential energy surface, projecting it on a simple parameter, it works. But when the process have a little bit complex potential energy surface, so by projecting it onto one simple parameter, even if this simple parameter can distinguish well between different states, so it might actually provide a very wrong estimation on the saddle points, actually. So Professor Delago already introduced, so actually the identification of reaction coordinate can really correlate to the committer probability. So committer probability is defined as the probability of a configuration starting at phase space to commit to the final state before coming back to the initial state. So actually it will provide us a statistical measurement of the reaction, and also it can provide us a model of the perfect reaction coordinate. So for the examination of the reaction coordinate, people always check the correlation between the committer and the collective variables. So what people often do is to calculate the committer at fixed values of collective variables, and then just check on the distributions of the committer. So if a collective variable is a good reaction coordinate, for example, so it should have a single sharp peak at certain value of committer. So for example, for a transition state, this should be picked at 0.5. And then if a collective variable is a poor reaction coordinate, then we might have a committer probability distribution that is widespread the whole range of the committer value. Oh, can you see my slides? Yes. Okay. So since crystal nucleation is a rare event, so actually there is a large free energy barrier separating between two states. So also the fast atomic motion and the crystal nucleation event, there is a time separation. So we cannot really use MD simulation. So therefore, actually in our case, we are using transition interface sampling. So basically this is a Monte Carlo sampling in phase space, and also we will harvest an ensemble of trajectories between liquid and solid. So in our GIS simulations, actually we are using the size of the solid cluster as an order parameter to differentiate between different states and also define our interfaces actually. And then I will introduce you a little bit about my system. So our system, we have around 7,000 atoms. In particularly, we have 75 atomic percent nickel composition there. And then we are using actually an EAM interatomic potential for nickel and aluminum. And then the condition we are simulating the crystal nucleation is specifically at 20% undercooling with respect to the melting temperature given by this EAM potential. And then for the solid liquid distinction, actually we are using Steinhardt order parameters to examine the local atomic environment around an atom. And then after we can identify solid atoms, actually we can count the numbers of solid atoms and then define the size of the solid cluster. So for the structure identification, so actually we are using averaged bond order parameters. So here I'm showing you a Q4, Q6 distribution map of nickel 3 aluminum. So basically based on this Q4, Q6 map, we can really identify really well different crystalline phases and then liquid in the nickel 3 aluminum. So after we did a TIS simulation and after we harvest ensemble of trajectories, so what we start to do at first is we start to analyze the structure fractions of the growing clusters. And then actually very interestingly, we saw there is a competing nucleation pathways existing, causing the small cluster where the small cluster can be dominated either FCC or either BCC phase. So for example, here I'm showing you structure fractions analyzed in cluster that is predicted as the critical size. And we don't really have a unimodal distribution of the structure composition, but instead, if you look at the FCC and then BCC phase fractions, actually these are bimodal. And when we check explicitly on the correlation of these two phase fractions, actually we saw these two phase fractions are actually mutually hindered, which means that the small clusters that are rich in FCC phase, actually it really has a very small amount in BCC and vice versa. And also, actually, we did MD simulations just taking these small clusters that are either FCC rich or BCC rich. And then we saw in the final solidification polymorph, actually it's really affected by the dominant phase fractions of the small clusters actually. So clearly there is a competing nucleation pathways existing in this nickel 3 aluminum. And then, so actually the size of the solid cluster cannot really provide us any additional information on the selected polymorph that appear in the crystal nucleation process. So then we start to think that, okay, then the solid cluster size, is it sufficient for us to serve or describe the crystal nucleation just using the cluster size? So we start to do the extensive committer analysis. So at first thing we did is from our related path ensemble, we just get the average committer projected on size. So as you can see, there's a very strong correlation between the average committer and the size of the solid cluster. So from the projection, it suggested the transition state or the critical size cluster will have a size of 427. So then we did a quantitative analysis, just taking the configurations with this size from our path ensemble. So what we did is we took 100 configurations with this size. And then for every configurations, we did 100 MD simulations and then compute the committer probability. So as you can see now, the committer probability has a distribution. That is not really a characteristic of the transition state peaking at 0.5, but actually it has a committer probability widespread all over the range showing multimodal. So this will indicate that actually in our case then, the size of the solid cluster is not really the optimum reaction coordinate for us to describe the crystal nucleation completely in this case. So since we already saw the competing crystalline phases when the small clusters grow, so we thought that, okay, then we need to maybe take into the account the impact of the crystallinity as the second component into the reaction coordinate. So we start to evaluate the crystallinity parameter. So basically it's also calculated from the Steinhardt order parameter. So this parameter will give us information on how structurally compact and well-ordered a solid cluster is. So now when we start to get the average committer projected on these two parameters, so as you can see, the average committer has a really strong correlation with both of these parameters. And in particularly, we saw that actually the transition state really has a nonlinear dependence on these two parameters. So in particularly, actually, the solid or the critical clusters, actually, it can be described with small size, but having large crystallinity And then the critical clusters can also have very large size, but very small crystallinity. So clearly, the inclusion of this crystallinity parameter really enhances the description of the reaction coordinate model. But then the problem also comes in that then actually, is it still sufficient when we combine these two as the reaction coordinate? And then now we took the configurations from our past ensemble based on these two parameters. So what we did is explicitly, actually, we took configurations that are suggested as the critical clusters described by size and crystallinity. So the clusters that are small in size and large in crystallinity. And then for this 214 configurations, for each configuration, we did 100 MD simulations, and then we calculate out the commuter probability. And now, actually, if you look at the probability, commuter probability distribution here, very interestingly, actually, we saw a bimodal distribution of the commuter. So there is one peak peaking at large commuter value. Oh, can you see my, sorry. Yeah. So there is one peak picked at large commuter value, and then there is also another peak picked at a small commuter value. So clearly, although the crystallinity actually improved the description into the reaction coordinate, but actually the combination of these two, it's still not sufficient to serve as the reaction coordinate to describe the crystal nucleation in this case then. So we start to think that then there must be another factor that is impacting the crystal nucleation process, causing this bimodal distribution of the commuter. And then we start to analyze the other collective variables for nickel 3 aluminum. So in particularly, we analyzed 22 parameters, 2 on size, and then 10 structural parameters, and then 10 chemical parameters. So within this 10, we have 8 parameters that describe the chemical composition, and then 2 parameters that describe the chemical order. So here I'm showing you an example where I'm showing you the correlation, or we plot the commuter probability as a function of structure parameters and then chemical parameters. So actually, since the crystallinity already captures the structure features relatively well, so for the other structure parameters, it did not really enhance the description for the reaction coordinate, showing very little correlation to the commuter probability. But then also very interestingly, actually, we saw that the chemical composition in this nickel 3 aluminum, actually, it does not change. We did not really see any phase separation. And then instead, the aluminum composition always stays at the optimum, stay near at the optimum value of 25%. And then the chemical composition does not really enhances the reaction coordinate to describe the crystal nucleation in our cases. So for the chemical order evaluation, so how we did it is actually when we try to calculate the chemical short range order within the emerging crystalline nuclei, actually we check on the normalized correlation of the site occupancy of the different chemical elements. So basically we can calculate the chemical short range order for different neighboring shells and then compare the results or compare the values with the reference values of L1-2 phases. So if a structure is chemically well ordered as L1-2 phase, so the chemical short range order in the first neighboring shell will be -1/3, and in the second neighboring shell, it will be 1. And since we analyzed 22 parameters, and then among these 22 parameters, so we saw very strong correlation between the commuter values and the chemical short range order. So explicitly, actually, we saw an increase in the commuter value following an increase when the small crystalline cluster having a chemical short range order towards L1-2 phase. So this actually gives us information that then the chemical short range order of the emerging nuclei might provide additional description into the reaction coordinate. And then as a next step, we started to do quantitative committer analysis, then based on these 3 descriptors. So now what we did is we just take configurations that is described by size and crystallinity. Of course, these 2 values we picked configuration at the fixed values and fixed crystallinity. And then among this, we took 2 compare sets. So they all have the fixed size and fixed crystallinity. But one set has large chemical order, another set has low chemical order. So for every configuration, again, we did 100 MD simulations, and then we compute the commuter probability. And actually very nicely, we saw a very clear separation of the commuter distribution. So at the fixed size and fixed crystallinity, actually we saw the clusters that has high chemical order will result in a high commuter probability promoting growth, and then the clusters that has low short-range chemical order will result in commuter distribution that has a peak near 0, which means these clusters shrinks. So this means that the chemical order within the small clusters really promote, really stabilize the solid cluster and then promote growth. So from all of our commuter analysis, then we see the effect of really the interplay between these 3 factors, in particularly the important factors that act as a multidimensional descriptors when we try to describe the crystal nucleation. So we really need a 3-dimensional descriptor to describe the complete nucleation process in nickel 3 aluminum system actually. So with that, I'm already at the end of my talk. So basically we did a TIS simulation, and then we did extensive commuter analysis of different parameters. And then what we saw is actually there is an existence of multiple reaction channel represented by a competition of FCC and BCC crystallite. So therefore the intuitive reaction coordinate, that is size of the cluster, is not really sufficient to serve or to describe the complete nucleation process. And then we need crystallinity as a second component to describe the crystal nucleation in nickel 3 aluminum. And on top of that, we also see the really key effect of chemical short range order, where the high chemical short range order will stabilize the small cluster and promote growth. And then the low chemical order will cause the cluster to shrink. And then we then conclude that actually in our nickel 3 aluminum system, we really need to take into account the interplay of these 3 parameters. One is size, and one is crystallinity, and another one is chemical short range order. So combining these 3 descriptors, we can describe the crystal nucleation correctly. So in general, we also would expect that in a multi-component complex system, the identification of a multidimensional reaction coordinate will be very crucial for us to understand the mechanism actually. Yes, so that's my presentation. Yeah, thank you.
Okay, Jan, thank you very much for this nice presentation. We have now, we are delayed, but we have time for a few questions.
Yeah.
I remind you again that if you want to ask a question, you can do that by indicating using the Q&A panel that you have in your Zoom window that you want to ask the question. Then we will open the microphone for you so that you can make it in live. So the first question here is by Simone Meloni.
Hi, Ignacio. So actually, my question is not a question; it's a comment, and it's not about Yan. Sorry, it's a general. I would say.
Yes.
I mean, it includes what you have told us about. So we often blame bad collective coordinates. My suggestion is that sometimes we don't have to blame them too much.
Okay.
One of the effects of wrong collective coordinates sometimes is hysteresis, but hysteresis is something that happens in nature. So imagine you accelerate your process by a collective coordinate which is not enough to get very well picked commuter at point 5. Still, you produce the process back and forth, and perhaps this collective coordinate is the same that a process back and forth, you stop at the same value of the collective coordinate and you just check what are the differences between the state of the system apart the collective coordinate that you are tricking. So this is telling to you perhaps what is producing the hysteresis, which is one of the questions that often experimentalists they want to know, either because they want to eliminate the hysteresis and so they want perhaps to act on the system to eliminate the source of hysteresis, or sometimes hysteresis is what they are looking after. I'm not referring, of course, to nucleation that you were talking about.
Yeah.
But there are many other processes. Some of them are also of technological relevance in which one wants to produce hysteresis, perhaps large hysteresis, and you would like to know how to control it, how to produce it. That's it.
Okay.
Yeah. Okay. Thank you. So,
thank you.
I don't know if there are any additional questions. I had a curiosity. I mean, you have learned that you have to expand these type of variables to have a better commuter. It almost seems as if, do you have an idea when to stop? Would you be wondering in looking for a fourth type of variable so that then still the commuter would be more clearly defined?
So for now, from this combination of 3 parameters, actually we can already see a really nice feature of like this picked distribution of the commuter. But of course, we really cannot really say if we are not really completely sure that this is the complete description. So of course, at first we need to really map or get the average commuter and then maybe project it on 3 parameters and then look at maybe what is the critical clusters that are described by these 3 parameters. And yeah, but I think because in this system, there is a really like different than the other metallics that are solid solution. So they always, I mean, in nickel 3 aluminum, they always have an this ordering tendency. So I think intrinsically it also comes into the play when the small clusters actually starts to crystallize.
Okay, thank you. Baron Peters also has a question.
Yeah.
Yes, I really appreciated the careful analysis.
Thank you.
Interesting application to the intermetallics. That's really great. I wanted to ask, I lost my scripted question here. I wanted to ask if it's possible to redefine the cluster size order parameter so that your clustering rule includes the effects of the short range order and local Q6 order, so that all 3 effects might actually become part of one nucleus size coordinate. And you know, if you could do that, the advantage would be an easier connection to nucleation theory.
Okay, so you mean that combining these 3-dimensional descriptors maybe into a 1-dimensional path collector variable or something, and then
so you have used a procedure, you know, I think probably going back to Frinkel for computing nucleus size, but you can use other clustering rules to compute nucleus size, and if they included SRO and local Q6, then they might count for many of the
other clustering algorithm. I didn't really get it actually. Sorry.
It's not the clustering algorithm, it's the criteria for deciding who gets included and who doesn't.
Okay.
And I just wonder if that's anything that you've tried.
So no, not now, no.
Okay.
Okay. I don't see any additional questions. So I think has been a quite long and very interesting session anyway. So I want to finish by thanking you for joining us, for having made this part of the session a success.